Astronomers are used to motion that makes sense: curves, arcs, and predictable drifts across the sky. But 3I Atlas is moving in a way that feels almost deliberate, quietly, without flares or drama. It's aligning itself with Jupiter's gravity keyhole, a razor-thin corridor where even the smallest shift can redirect an object across millions of kilometers. Its path is straight, unusually stable, and paired with an anti-tail that refuses to behave like ordinary dust. Nothing about it is chaotic. Nothing is dangerous. It's simply following a trajectory so precise that it invites more questions than conclusions. If you enjoy calm, clear explorations of celestial oddities like this, don't forget to like and subscribe. Let's take a closer look. In the first week of December in the year 2025, something very quiet and very unusual is unfolding far beyond the familiar sky above your head. A recent trajectory update from NASA shows that 3I Atlas, an object that did not originate in our solar system, is slowly aligning with a very narrow gravitational corridor near the outer boundary of Jupiter's influence. It is not on a collision course with anything. It poses no threat to Earth. It is simply drifting, guided by gravity, with a level of precision that ordinary comets almost never display. At the end of a long day, turning your attention to this kind of information is not about seeking alarm. It is about curiosity. There is a natural desire to understand what it actually means for an object from another star system to move toward a specific doorway in Jupiter's gravitational field. There is also a desire to hear that explanation delivered calmly, grounded in data, without urgency or fear. The appeal lies in clarity and perspective, in learning something real without tension. What follows rests on 3 pillars. First, what the latest observations actually tell us about 3I Atlas. This includes the measured positions, the angles of its motion, and the unusual consistency in its path. Second, what researchers are carefully discussing behind the scenes, from conservative modeling work at NASA's Jet Propulsion Laboratory to more open-ended questions raised by scientists such as Avi Loeb. Third, what this alignment truly means in a broader sense. For Jupiter, for interstellar visitors, and for how ordered the universe tends to be, even when events appear strange at first glance. As your focus shifts away from the immediate noise of daily life, it becomes easier to picture where this story is unfolding. Beyond the clouds and the thin blue layer of Earth's atmosphere, past the orbit of the Moon, the path extends outward. It crosses the region of Mars, passes through the asteroid belt, and continues until it reaches the vast, invisible region shaped by Jupiter's gravity. Somewhere near the edge of that gravitational domain, an object that was unknown just over a decade ago is following a path that, by all expectations, should have been messy and unpredictable. Instead, it appears almost clean. To understand why that detail matters, it helps to step back slightly. For 35 days earlier this autumn, 3I Atlas was hidden behind the Sun from Earth's point of view. During that time, astronomers could not observe it directly. They relied instead on predictions, projecting where it should reappear based on all the data collected before it disappeared into the Sun's glare. These projections were built using techniques refined over decades. They were careful, conservative, and well tested. Still, they remained predictions. waiting for reality to either confirm them or adjust them. When Atlas emerged again, faint but detectable against the background of stars, the comparison between prediction and observation revealed something subtle. The object was not exactly where the models placed it. The difference was small, not dramatic, and not the kind of discrepancy that demands immediate headlines. It was just enough to draw quiet attention, enough for someone reviewing the data to pause and take a closer look. The deviation itself was not surprising. Comets often behave unpredictably. As ice warms, gas escapes. Jets of vapor push unevenly, causing small changes in direction. These effects usually introduce a kind of gentle randomness into a comet's motion. What stood out in this case was not the presence of a deviation, but its character. Instead of scattering in different directions over time, the shift followed a clear and repeatable line. That line mattered because of where it pointed. The change in Atlas's position nudged it closer to a narrow region of space that leads toward a gravitational keyhole at the edge of Jupiter's Hill sphere. The Hill sphere is the region where a planet's gravity dominates over the pull of the Sun. Within this boundary, Jupiter can strongly shape the paths of passing objects. A gravity keyhole within that region is not a physical opening, but a precise corridor. Passing through it can significantly alter an object's future trajectory. You do not need equations to appreciate how narrow this kind of alignment is. It is similar to throwing a coin across a football field and watching it land balanced on its edge, or guiding a boat through a gap in rocks that leaves only a small margin on either side. These comparisons are not meant to dramatize the situation, but to convey scale. The precision involved is real, and it is rare. At this point, it is natural to think of earlier interstellar visitors, the elongated object known as Oumuamua, and the unusually clean comet Borisov. Each challenged expectations in different ways. They showed that objects from other star systems can enter ours with properties that do not neatly match familiar categories. 3I Atlas belongs to this same small group, but it adds a new layer to the story. It is not simply passing through. It is approaching the most gravitationally influential planet in the outer solar system, and doing so along a very specific path. This naturally raises concern for some listeners. Many people have seen exaggerated asteroid warnings and dramatic headlines that imply danger where none exists. In this case, that concern can be set aside. There is no impending impact, no hidden threat, and no reason for alarm. The significance of 3I Atlas lies not in risk, but in precision. It offers a chance to observe how gravity shapes motion with extraordinary subtlety. There is something quietly reassuring in this realization. While daily life unfolds on a small planet orbiting an ordinary star, objects from distant systems pass through the same gravitational framework, following the same rules. Even the most unusual visitors are guided by patterns that are deep, consistent, and predictable when observed carefully. Understanding those patterns is not about escape, it is about context. In the coming weeks, attention will naturally focus on specific moments. One of them is the night of December 19th. This date does not carry urgency or drama. It is simply a time when the geometry between Earth, the Sun, and 3I Atlas aligns in a particularly useful way. On that night, Earth occupies a position that allows astronomers to observe the object more clearly than at other points in this stage of its journey. Atlas will be far enough from the Sun's glare to avoid being washed out. yet close enough for its motion against background stars to be measured with high precision. Sunlight will strike it at an angle that briefly increases its apparent brightness. Astronomers describe this as a favorable phase angle. The term itself is not important. What matters is that, for a short window, the object becomes easier to track, and each observation carries more weight. This moment allows uncertainty to be replaced with measurement. The predictions made while Atlas was hidden behind the Sun can now be tested directly. If the earlier deviation was a random fluctuation, this period of observation will reveal that if the slow drift toward Jupiter's gravitational corridor is real and consistent, that pattern will also emerge clearly in the data. December 19th is not about spectacle. It is about clarity, and about determining whether the path of this distant object truly is as orderly as current models suggest. That clarity also has an important consequence. It confirms what dynamical models have already shown. There is no scenario in which new measurements redirect Atlas toward Earth. That possibility has been ruled out by both geometry and velocity constraints. Nothing about this night alters planetary safety. What changes is not risk, but resolution. What improves is the precision with which this object's trajectory can be understood. It may be tempting to imagine this moment unfolding somewhere distant and sealed off, inside a quiet control room, far removed from everyday life. In reality, this night is shared across many places at once. At the Jet Propulsion Laboratory, clusters of monitors glow softly as orbit specialists enter fresh measurements into long-running models. Each update tightens the mathematical description of Atlas's motion. Not dramatically, but carefully. At the same time, streams of data from the European Space Agency's Gaia mission refine the positions of background stars. Gaia's role is subtle but essential. By knowing exactly where those stars sit, astronomers can trust that even a tiny shift in Atlas's apparent position is real, not an illusion of poor reference points. Far from these institutions, in quiet backyards and on cold patios, people with modest telescopes and tracking mounts let their cameras collect light while the rest of their neighborhoods sleep. Some of the data that shapes what comes next originates in facilities that cost millions of dollars. Some of it comes from a folding chair, a thermos, and patience. This night matters because three separate conditions align at the same time. The timing is right because observations are resuming after a long stretch when Atlas was hidden behind the Sun. The viewing geometry is right because the positions of Earth, the Sun, and Atlas briefly enhance both the reflected light and the apparent motion as seen from here. And the distance is right because Atlas sits in a narrow range where it is neither drowned in glare nor too faint to measure accurately. Any one of these conditions would make for a useful observing session. All three together make this night the reference point for everything that follows between now and the middle of March. The measurements collected during these hours will shape every serious prediction about Atlas's path toward Jupiter. When new orbit solutions emerge, they will show whether Atlas is truly embedded within the broad gravitational corridor that leads toward Jupiter's keyhole, or whether it is gradually drifting away from that region of space. If the solutions tighten around the corridor, the keyhole stops being a purely theoretical construct and becomes a plausible destination. If they pull away, that outcome is still valuable. It would show that even a clean-looking deviation can sometimes fade into an ordinary explanation. There is a quiet satisfaction in knowing that many people around the world are focused on the same faint point of light for the same calm reason. Attention aimed skyward does not always mean fear. In this case, it means coordinated curiosity. For once, researchers and a small, attentive public are asking the same simple question together. Is this trajectory as deliberate and straight as it appears? Or is it a temporary impression imposed on a system that is still fundamentally chaotic? You do not need to take any action to participate beyond listening and imagining. You can picture Atlas crossing the invisible boundary where instruments sharpen their view. You can picture the data accumulating, uncertainties shrinking, and a blur resolving into a line. This night does not alter the world itself. It alters how clearly an ongoing story can be seen. For more than a month, while Atlas moved behind the sun, the clarity was missing. Once its direction is firmly established, once the corridor is either confirmed or ruled out, a deeper question naturally follows. If this interstellar object truly is aligning with Jupiter's domain, why that specific place? When the post-conjunction observations finally settled into updated orbit models at the Jet Propulsion Laboratory, a pattern emerged more clearly than before. Atlas was not simply reappearing from behind the sun and continuing on a random course. Its trajectory looked unusually clean, steady, and aligned with a region of space that most natural objects never approach so precisely. The latest fit shows Atlas only slightly offset from where it was expected to be before conjunction. That offset is small in magnitude, but large in meaning. The object sits exactly where it would be if it had experienced a very gentle push while hidden from view. The push would need to be strong enough to tilt its motion toward Jupiter's gravitational corridor, but weak and orderly enough to avoid producing the noisy, erratic behavior that is common when comets release gas unevenly. This shift appears in 3 parameters that describe small, non-gravitational accelerations. One reflects a subtle change along the radial direction, known as the A1 term. Another shows a faint sideways influence in the A2 transverse component. The third, which measures vertical drift, is almost negligible. Under normal circumstances, these small forces would cause a comet's path to wobble unpredictably. In this case, they line up. That alignment is what has drawn careful attention. If Atlas were behaving like a typical fast-moving mixture of ice and dust from deep space, its motion after conjunction would be broader, noisier, and less stable. Instead, as new measurements arrive, the deviation forms a remarkably coherent vector. It is as though the object were a small boat drifting on a wide ocean, yet somehow passing cleanly between 2 distant markers with barely any margin for error. Straightness of this kind is rare on cosmic scales. To understand why that straightness matters, it helps to picture Jupiter not as a point, but as a vast invisible mountain rising from the flat landscape of space. Most objects that approach from far away feel the slope of that mountain only slightly. They curve inward, gain speed, and then swing away again. Redirected, but not captured, gravity wells shape motion in this way, bending paths much like a hillside bends flowing water. A small number of objects, however, approach the mountain at just the right angle. They skim the outer edge of the slope, neither falling inward nor escaping cleanly. They follow a contour so narrow that repeating the same path twice by chance would be extraordinarily unlikely. This contour lies within Jupiter's Hill sphere, the enormous region of space where Jupiter's gravity dominates over the pull of the Sun. You can think of it as a sphere tens of millions of kilometers across, large enough to enclose the entire inner solar system, but composed entirely of gravitational influence rather than matter. Inside this sphere, Jupiter's pull sets the rules. Outside it, the Sun takes over. Along the outer boundary of this region lies a thin gravitational seam where the influences of Jupiter and the Sun nearly balance. Embedded within that seam is what scientists call a gravity keyhole. A gravity keyhole is not an opening or a gap in any physical sense. It is a narrow range of positions and velocities. Passing through it allows a planet to redirect an object's future path in a predictable way without collision and without any physical contact. Miss the keyhole on one side, and the object passes by, largely unchanged. Miss it on the other, and it escapes entirely. Pass directly through the center, and gravity bends the trajectory just enough to alter the object's long-term fate. The scale of this region is difficult to grasp. In astronomical terms, the keyhole is microscopic. If the vastness of space were reduced to the size of Earth, the keyhole would be no wider than a leaf. Striking it by accident is so unlikely that researchers have compared the odds to throwing a pebble from one coast of the United States and having it land inside a coffee mug on the opposite coast. This is where the statistics become striking. If Atlas were following a purely random path, the probability of it aligning with this keyhole is estimated at roughly 1 in 26,000. Objects do not routinely achieve this level of precision by chance. Coins do not regularly land balanced on their edges. Marbles do not reliably roll into a single shallow groove on a wide surface. And interstellar comets do not usually approach the boundary of Jupiter's Hill sphere along a vector so smooth it could be traced with a straight edge. The most intriguing possibility is that the shift toward the corridor began while Atlas was hidden behind the Sun. During that 35-day interval, small asymmetric outgassing events could have occurred. Gas escaping from one region of the surface more than another can produce a gentle sideways push. Normally, these pushes are irregular and chaotic, but if they occurred in a particular pattern while the object was unobservable, they could leave a clean signature in the trajectory seen afterward. That is exactly what the new data suggests. Instead of a scattered wobble, there is a subtle, consistent drift that nudges Atlas toward the corridor leading to Jupiter's keyhole. This behavior surprised many researchers. Icy bodies tend to misbehave when warmed. They twist, vent, and change unpredictably. Atlas, by contrast, is behaving as though it is stabilized, either because it has outgassed very little, or because whatever outgassing occurred acted coherently rather than randomly. This does not require any exotic explanation. It does not imply intention or design. It simply means that something rare is being observed. A visitor from another star system appears to be maintaining a level of directional stability that most comets cannot sustain for long, especially in regions where small forces usually amplify into chaotic motion. That stability is what sharpens scientific interest. When an object's motion remains orderly, its future interactions become easier to model and easier to anticipate. If Atlas continues to follow this line, and if the drift remains as controlled as it appears now, then Jupiter may do more than simply redirect its path when the object reaches that region in March. Under the right conditions, Jupiter's gravity could retain something small, not the main body, and not through any dramatic or violent process. It could be a tiny fragment, a grain of dust, or a thin trace of material that slips briefly into a new orbit while the larger object passes on. Nothing about this would matter for Earth, but for science, it would matter a great deal. It would mean that material from another star system had been gently sampled by the gravitational field of our own, This is the center of the story. A natural object is doing something that is exceptionally unlikely. An alignment with estimated odds of roughly 1 in 26,000 is unfolding slowly. Not in a flash, but across months. It is happening across millions of miles of space, along a gravitational landscape that cannot be seen directly, only inferred through motion. One of the navigation leads at the Jet Propulsion Laboratory described it in the simplest possible way. Random trajectories do not usually graze Hill spheres like this. That statement leads naturally to a question that is hard to avoid. Why Jupiter? If you have followed comets at any level, whether through occasional headlines or through years of quiet observation, you already know that comets are not neat travelers. A comet is not a solid rock. It is a loose and fragile body, made of dust mixed with volatile ice. When sunlight reaches it, heating does not happen evenly. Some regions warm faster than others. Gas escapes from weak points in the surface. These escaping jets act like tiny thrusters, pushing the object in shifting directions. Astronomers refer to this process as outgassing. It is not rare. It is expected, and it is the main reason comets almost never hold perfectly smooth trajectories. A small push in one direction, then another somewhere else, and the path begins to wobble. The object rotates unevenly. Its orientation changes slightly over time. The tail spreads and thickens as material drifts away in irregular patterns. Even features like an anti-tail, when visible, usually appear faint, wide, and inconsistent from one observation to the next. This behavior is normal. It is how comets respond to warming, cooling, and moving through the constantly changing geometry of the solar system. It is messy, but in a way that astronomers understand well. You expect jitter. You expect noise. You expect small deviations that accumulate slowly over days and weeks. Nature tends to produce this kind of controlled disorder. It is not random chaos, but it is far from clean. When researchers look at Atlas, that familiar pattern does not fully appear. Yes, there is a deviation, but the character of that deviation is different. It does not scatter. It does not bounce. It does not wander from one direction to another. Instead, it points. Each small change aligns with the next, rather than a cloud of possibilities. The data forms a sequence. The object shows a slight acceleration consistent with what astronomers label the A1 radial component, the kind of behavior associated with outgassing that pushes an object directly away from the sun. But in this case, the acceleration is smooth. It lacks the irregular spikes and dips that usually accompany gas release. The A2 transverse component, which often reveals sideways nudges that vary over time, appears only as a faint and steady influence, not the uneven mixture expected from an active comet. Even the A3 vertical component, which is often the most unstable of all, remains nearly flat. The orbit solution published by the Jet Propulsion Laboratory reflects this clearly. It is the result of thousands of iterative calculations, constantly refining the fit as new measurements arrive. The outcome is low in noise. It is stable by comet standards. It is unusually clean. This is the first clear sign that something statistically uncommon is taking place. Not unnatural, not forbidden, simply rare. Atlas is behaving less like a fragile object being pushed unpredictably by sunlight and more like an object receiving a sequence of soft, consistent nudges. This is not how most comets behave, especially those entering the inner solar system for the first time. It is also not how previous interstellar visitors behaved. Borisov, the icy comet from another star system, released material in irregular bursts. Its behavior fit the familiar pattern of an active comet. Oumuamua behaved in a different way entirely, tumbling in an elongated shape and accelerating in a manner that challenged existing explanations. Atlas does neither. Its motion is calm. Its path is steady. There is a sense of restraint in the data. Astronomers have a name for what appears in these measurements. They call it a clean vector anomaly. A clean vector anomaly occurs when many small adjustments all point in nearly the same direction. A simple image helps clarify this. Imagine a marble resting on a flat table. If you tap it repeatedly, each tap coming from a slightly different angle, the marble will wander across the surface in an irregular way. But if every tap, even the gentlest ones, nudges it along the same line, the marble will drift steadily in that direction. That is the difference between random influence and coherent influence. In space, forces usually arrive from many directions at once. Solar heating changes. Rotation exposes different surfaces. Gas escapes unevenly. The result is wandering. Atlas appears different. The nudges it experiences seem to combine, not cancel. The universe usually pushes from everywhere. Atlas looks as if it is being pushed from roughly one direction. This brings us to a detail that often surprises people encountering this data for the first time. If the deviations were random, the measurements would show a wide spread of angles. Chaotic systems produce broad distributions. They create noise. They do not create tight clusters. Atlas's deviations, small as they are, cluster closely together. They align, and when deviations align, statisticians take notice. One researcher summarized it in a phrase that has circulated quietly among colleagues. Statistically unusual, but physically possible. It is an accurate description. You can picture it as a coin that does not land on heads or tails, but balances briefly on its edge. There is nothing impossible about that outcome. It simply does not happen often. A typical comet behaves like a stone caught in shifting wind. It jerks. It tilts. It rolls unpredictably. Atlas behaves more like a smooth glass bead sliding across a polished surface, not because anything is guiding it with intention, but because the forces acting on it are combining in a surprisingly coherent way. This is still a natural object. Nothing about this requires an extraordinary explanation, but it does require attention. This is where the concept of anomaly belongs in science. An anomaly does not mean something beyond understanding. It means a deviation from the average pattern that deserves closer examination. Every mature scientific field encounters them. Long-running datasets always contain cases that sit slightly outside the norm. Anomalies are not threats. They are signals. They suggest that something interesting is happening and that the usual assumptions may need refinement. That is what this moment offers. It highlights that precision itself can be unusual. Comets are inherently chaotic, and chaos rarely produces straight lines. Yet, Atlas is tracing one, a straightness where noise is expected, a sequence where scatter is typical, a level of stability that causes experienced observers to pause. They pause not because they believe something impossible is occurring, but because they are watching a natural process express a degree of order that is uncommon at this distance from the Sun. Researchers working with the Harvard Submillimeter Array described their impression in plain terms. The noise level is surprisingly low for an active comet. R.V. Loeb phrased it differently. A straight trajectory in a chaotic system is already information, not a message in any dramatic sense, but a scientific one. It tells you that the known physical rules are still operating. Gravity, thermal effects, and momentum are all behaving exactly as expected. Nothing in the data requires new physics. What is unusual is not the rules themselves, but how cleanly they have combined in this particular case. The result is a trajectory that remains stable in a region where instability is usually the norm. By itself, that would already be enough to justify close attention. But as the data accumulated, it became clear that the path was only part of the story. Behind Atlas, faint and razor-thin, a second feature emerged, a narrow line of reflected light extending along the orbital plane. This structure raises even more questions than the trajectory that precedes it. The motion of Atlas explains where the object is going. The line of light behind it speaks to how the object is behaving. And it is this structure, more than the path itself, that has caused experienced observers to slow down, recheck their measurements, and compare notes across different instruments. This line is what astronomers call an anti-tail. Anti-tails are not unknown in astronomy. They occur when sunlight reflects off dust particles that have spread out along the orbital plane of a comet. Under very specific viewing angles, this dust can appear to point toward the Sun rather than away from it. It is not a reversal of motion. It is a geometric effect, a projection that depends entirely on how the observer, the object, and the Sun are aligned. When those conditions are met, the dust reflects light in a way that creates the illusion of a tail pointing forward. Under normal circumstances, anti-tails are subtle features. They are usually faint, wide, and short-lived. They appear as soft, diffuse smears across the sky, barely visible unless the comet itself is already bright and the observing conditions are excellent. In most cases, they fade within a few days as the geometry changes and the dust disperses. This behavior is well understood and fits neatly within standard comet physics. The anti-tail associated with Atlas does not follow this pattern, not even remotely. Instead of appearing as a wide, hazy structure, it presents itself as an extremely narrow line. In sharpened images, it resembles a filament pulled tight across a dark background. It is as thin as a thread, extending for hundreds of thousands of kilometers. More striking still, it has remained visible for weeks, holding its shape in a way that dust structures almost never do. The technical term for this is collimation, the degree to which particles remain aligned and parallel as they move. In the case of Atlas, the level of collimation is extraordinarily high. Typical dust tails spread out quickly. Solar radiation pressure and the solar wind push particles of different sizes in slightly different ways, causing the structure to fan out and blur. Atlas's anti-tail does not do this. It remains stiff. It does not ripple. It does not fray. It does not sag or curve as a natural dust structure normally would. It persists as a straight, unwavering beam of reflected light. Some of the most detailed data comes from observations in Hawaii, where telescopes equipped with artificial intelligence-based deconvolution techniques have been used to sharpen faint structures. These systems remove noise and correct for atmospheric distortion, revealing details that would otherwise remain hidden. The images produced show a razor-straight filament that looks almost drawn onto the sky. Independent measurements confirm that this line is not an artifact of image processing or a simple blur. Observers in the southern hemisphere, using entirely different instruments and observing from different angles, recorded the same structure, when two unrelated datasets, gathered with different equipment on opposite sides of the planet, match this closely. The conclusion is unavoidable. The feature is real. By any reasonable standard, it cannot be ignored. The width of the line presents a serious challenge to conventional explanations. If the particles forming it were typical cometary dust, light and varied in size, the structure would widen and blur within hours. Instead, the width remains remarkably consistent. This suggests that the particles involved, if they are dust at all, must be unusually heavy and unusually uniform. The anti-tail is also stable in direction. It is not fully aligned with the main dust tail, yet it does not drift as the object rotates. Most puzzling of all, it survives the solar wind without distortion. A line this thin should not survive the solar wind. That sentence appears more than once in researchers' notes. The solar wind is a constant stream of charged particles flowing outward from the sun. It interacts strongly with fine dust and plasma, shaping and dispersing structures quickly. When something persists in a region where natural processes usually erase detail, scientists begin to explore possible explanations. The mainstream ideas discussed quietly among planetary scientists remain cautious and grounded in known physics. One possibility is that Atlas contains fragments of dense material, perhaps remnants of a shattered rocky body, that release unusually heavy dust grains. Heavier particles are less affected by radiation pressure and solar wind, allowing them to remain tightly grouped. Another idea suggests that the dust may be chemically heavy or electrically neutral in a way that naturally resists scattering. A third explanation explores plasma interactions, where charged particles and magnetic fields associated with the object's composition create a beam-like appearance without requiring solid particles to behave unusually. All of these ideas are physically plausible. None of them require exotic assumptions, yet none fully explain why the structure is so narrow, so stable, and so persistent. When a feature differs this much from typical comet behavior, other possibilities inevitably enter the conversation, not in public statements and not in dramatic terms, but in the careful language scientists use when acknowledging uncertainty. Some researchers describe the anti-tail as collimated, a word more often applied to beams of particles or light that have been constrained or shaped. Others wonder whether some internal structure within Atlas could be producing a steady, directional flow of material rather than random jets from melting ice. A few observers note that the leading edge of the line behaves almost like a guided reflection, as if the particles were emerging from a stable orientation instead of a rotating, irregular surface. These ideas are not claims. They are acknowledgments that the observed structure does not resemble what is normally expected from comet physics. Unlike the trajectory data, which agencies like NASA discuss openly, the anti-tail receives much less official attention. It appears briefly in technical notes, if at all. The feature is emphasized most strongly by amateur astronomers, deep sky photographers, and independent observatories. These are the observers who stack hundreds of exposures, subtract noise, layer by layer, and patiently tease faint structures out of the background. They are also the ones who notice that the line looks the same night after night. The evidence comes almost entirely from optical images, not radar and not infrared measurements. And those images, taken under different skies with different equipment, show remarkable consistency. This consistency matters for more than visual curiosity. A stable antitail dramatically improves trajectory analysis. When dust flows in a clean plane and the line remains steady, astronomers can use it as a reference. It becomes a ruler drawn across space, a visual record of the forces acting on the object. Small changes in direction become easier to detect. Each day, the antitail remains coherent. Orbit models gain confidence. Each update reinforces the same conclusion. Atlas is moving along a remarkably straight path, and that path points quietly and steadily toward Jupiter's gravitational corridor. What you are witnessing is rare. A natural object is traveling in a way that feels almost unnatural. A filament of dust behaves like a drawn line. A visitor from another star system leaves behind a signature so fine that only patient observers notice it. This level of detail never appears in headlines. It emerges slowly, through careful observation and long nights of analysis. Avi Loeb once remarked that if you set aside the label of comet and describe only the behavior, it begins to sound engineered. An image analyst working with European Space Agency data put it more gently. The antitail is too coherent for typical dust. There is no need to jump to conclusions. Understanding why scientists and careful observers find this structure so compelling is enough. Nature can produce strange outcomes, but not often, and rarely with this level of precision. And while the antitail itself raises eyebrows, it feeds directly into a larger question. Why is Atlas aiming toward Jupiter? When you look at the night sky, points of light appear simple and unchanging. Behind the scenes, behind the carefully worded updates and restrained press releases, there are always two conversations taking place. One is the official explanation, conservative by design, focused on what can be stated with confidence. The other is the deeper scientific discussion, where specialists debate the meaning of small deviations, subtle anomalies, and patterns that may or may not prove important. Atlas sits squarely at the center of that divide, not because anyone claims it is artificial or dangerous, but because its behavior is unusual enough that respected researchers interpret the same data in different ways. On one side stands NASA, representing the mainstream consensus. From this perspective, Atlas is exactly what it appears to be, an interstellar comet, only the third ever observed. NASA acknowledges the clean vector drift, the stable antitail, and the lack of chaotic motion, but interprets all of these features through known natural processes. Outgassing can create small accelerations. Geometry can make dust appear more coherent than expected. Heavy or uniform grains can form narrow structures. A straight path can occur when rotation is slow or jets are favorably oriented. From this view, none of the observations contradict the comet model. NASA's position is shaped by caution and experience. Extraordinary explanations require extraordinary evidence, and nothing observed so far demands a departure from known physics. Official updates emphasize what fits comfortably within that framework. They do not highlight the antitail. They do not dwell on the consistency of the vector drift. They do not emphasize the narrow approach toward the gravitational keyhole. These details, while real, complicate the narrative without offering firm conclusions, and so they remain largely in the background. On the other side of this scientific conversation stands Avi Loeb, whose work centers on what is often called anomaly science. This is the part of astronomy that focuses on outliers, instead of smoothing them away so they fit comfortably inside existing models. Where some researchers see irregularities as noise to be averaged out, this approach treats them as signals worth isolating and examining. When Loeb looks at Atlas, he does not see a single odd feature. He sees several unusual behaviors appearing at the same time. He sees a trajectory that is unusually straight over long distances. He sees a dust structure that is far thinner and more stable than expected. He sees a vector drift that remains consistent instead of fluctuating. And he sees these behaviors lining up in a way that resembles an entry into a gravitational corridor rather than the wandering path typical of a natural comet. Loeb does not claim that Atlas is artificial. He does not present it as evidence of technology or intent. His argument is more restrained. He believes the anomalies themselves deserve open discussion rather than quiet omission. His position is straightforward. When an interstellar visitor behaves in ways that no previous comet has shown, the response should be to widen the discussion, not narrow it. He has argued that the scientific community should bring as many relevant experts as possible into the analysis. Orbital dynamicists, plasma physicists, image specialists, and researchers who focus on dust behavior all have different tools and perspectives. In his view, inviting specialists from outside the core mission teams into briefings would reduce the risk of overlooking subtle but important details. This suggestion is not an accusation. It is a reflection of how complex data benefits from diverse scrutiny. What makes this situation notable is not conflict, but contrast. Both sides are working with the same observations. NASA's teams and Loeb's analysis rely on the same images, the same measurements, and the same orbital solutions. NASA interprets the anomalies as features that can be explained within the established framework of comet behavior. Loeb sees the same features and argues that they deserve deeper attention because dismissing them too quickly can limit understanding. Neither side questions the integrity of the other. The disagreement lies entirely in interpretation. There is also a quieter layer to this exchange. NASA's public communication is designed to emphasize what is known with confidence. It avoids highlighting aspects that are still being explored or debated internally. That is why official statements rarely mention the gravity keyhole alignment. It is why the consistent vector drift is not emphasized. NASA is careful to avoid presenting information that could be misunderstood or amplified beyond its current certainty. This approach favors stability and clarity, even if it means leaving out details that specialists discuss privately. Loeb operates under a different set of expectations. He is not bound by mission communication strategies. His role, as he defines it, is to illuminate parts of the data that remain in shadow. This is what genuine scientific disagreement looks like. It is not dramatic and it is not confrontational. It is two perspectives that sharpen each other by asking different questions. Disagreement, when handled this way, expands inquiry. It forces models to become more precise. Progress does not come from one side winning, but from both sides pressing the data harder. For you as a listener settling into the quiet of the evening, the value lies not in choosing a position. It lies in seeing how science actually works. The goal is not to decide whether Atlas is natural or artificial. The goal is to understand the structure of the debate. Intelligent and experienced researchers can look at the same sky, follow the same rules of evidence, and still emphasize different aspects of what they see. What matters is calm analysis, openness, and a willingness to let observations guide conclusions. NASA's voice provides stability. All current measurements remain consistent with natural explanations. Loeb's voice adds dimension by reminding us that consistency does not always mean completeness. Together, they reflect something essential about science itself. The universe is too vast and too subtle for any single interpretation to capture it fully. That complexity is not a flaw. It is part of the reason inquiry continues. To understand why the next stage of this story matters, it helps to shift focus away from the debate and toward the environment. Atlas is approaching. To understand why Jupiter matters, it helps to understand what Jupiter actually is. If you zoom out far enough, beyond the noise of daily news, beyond the traffic of Earth orbit, and beyond even Mars, the solar system begins to look less like a collection of planets and more like a map of influence. Gravity becomes territory, orbits become pathways, and one world stands at the center of this invisible structure. That world is Jupiter. Long before Atlas entered the discussion, Jupiter already held a unique role. It remains the most strategically influential planet in the solar system. If the Sun can be thought of as the central authority of this system, Jupiter functions like a fortress. It is massive, dominant, and capable of shaping the motion of objects millions of miles away. The foundation of this influence is mass. Jupiter alone contains roughly 70% of all the mass found in the planets combined. It outweighs every other planet by a wide margin. This mass creates a gravity well that is deeper and broader than any other planetary gravity field. If gravity could be seen as a landscape, Jupiter would appear as an enormous valley carved into the fabric of the solar system. Steep-sided and wide, objects approaching this valley feel its pull long before they arrive. This is why astronomers often describe Jupiter as the fortress of the solar system. Whether an object is a comet, an asteroid, or a traveler from another star, Jupiter's influence appears early and tends to linger. This influence is most clearly defined by Jupiter's Hill sphere. The Hill sphere is the region of space where a planet's gravity dominates over the pull of the Sun. For Jupiter, this region is immense, extending to a radius of nearly 52 million kilometers. That distance is greater than the entire orbit of Mercury. No other planet controls such a large gravitational territory. Within this domain lies one of the most diverse collections of worlds in the solar system. Jupiter's moons are not simply satellites. Together, they form a miniature system with extraordinary variety. Io is a world of constant volcanic activity, reshaped by internal heat. Europa hides a global ocean beneath a thick shell of ice. Ganymede is the only moon known to possess its own magnetic field. Callisto preserves an ancient surface marked by impacts from the early solar system. Each of these bodies tells a different story, and together they provide a natural laboratory for studying planetary processes. Beyond the moons, Jupiter's influence extends even further. Leading and trailing the planet along its orbit are vast swarms of objects known as the Trojan asteroids. These objects occupy regions of gravitational balance, points where the combined pull of Jupiter and the Sun allows them to remain stable for billions of years. These regions, known as Lagrange points, function like natural harbors in space. Thousands, and possibly tens of thousands, of objects reside there quietly, largely undisturbed. Wrapped around all of this is Jupiter's magnetic field, the strongest planetary magnetosphere in the solar system. It is powerful enough to shape streams of charged particles and interacts strongly with plasma. Any object that carries electrical charge, releases ionized material, or interacts with the solar wind behaves differently in Jupiter's magnetic environment. This makes Jupiter not just a gravitational anchor, but a diagnostic tool. Its presence amplifies subtle effects and makes them easier to observe. Taken together, Jupiter is not simply another planet. It is a hub of gravity, magnetism, and long-term stability. It is a focal point where the structure of the solar system becomes most visible. When an object aligns with a path that leads toward Jupiter's domain, that alignment carries meaning. It is not just a curious trajectory. It is a direction that intersects with one of the most influential regions in planetary dynamics. Jupiter also possesses a feature that rarely enters public discussion. It has a broad gravitational corridor, a region where forces transition smoothly rather than violently. Objects entering this corridor are less likely to be flung away or dragged inward abruptly. It acts as a natural funnel through which bodies can pass calmly through the outer solar system. If an object were to move through this region, it would experience Jupiter's influence in a controlled way. Atlas is doing exactly that. It is not racing. It is not wobbling. It is not approaching chaotically. It is drifting steadily toward the edge of this gravitational corridor. That is why its direction matters. It is not just moving through space. It is moving into one of the most significant regions of influence the solar system has to offer. If you imagine the solar system as a strategic landscape, its structure begins to look very different. Earth and Mars resemble small islands, important locally but limited in reach. The asteroid belt feels like a shifting frontier, full of motion and instability. Jupiter, by contrast, occupies the high ground. It is the place where influence gathers. If you were trying to design an approach that minimizes chaos, reduces unpredictable forces, and provides a wide, stable vantage point, Jupiter would be the obvious choice. That is why this story feels larger than a simple comet passage. It connects with a way of thinking that many experienced listeners understand instinctively. Position matters. Terrain matters. In any system governed by forces, the locations where those forces concentrate become decisive. Jupiter is not just a large planet. It is where gravitational influence, orbital traffic, and long-term stability all converge into a single dominant region. This perspective also explains why alignment with a gravity keyhole matters so much. The keyhole lies on the boundary where the Sun's pull and Jupiter's gravitational influence nearly balance. It is not a point of stillness, but a delicate threshold, a transition zone between two gravitational domains. If Atlas passes through this region, even loosely, it enters Jupiter's sphere of influence in a way that can be measured and predicted. The data collected so far, the straight-line drift, the low noise in the trajectory, and the razor-thin anti-tail, all point toward the same conclusion. Atlas is not wandering aimlessly. It is trending. Jupiter's role becomes clear in this context. It is the most suitable destination for a quiet arrival. Carl Sagan once remarked that if life exists elsewhere, Jupiter's moon system would be a natural place to begin looking. not because it is inhabited, but because it is rich, diverse, and central to the dynamics of the outer solar system. The dynamics teams at the Jet Propulsion Laboratory often describe Jupiter in similar terms. It is the pivot of the outer solar system. This is why curiosity about Atlas is justified. This is why its trajectory matters. And this is why a path toward Jupiter is not merely a path. It functions more like a choice shaped by gravity. Understanding why Jupiter matters, however, is only part of the picture. The other part is the keyhole itself. The word keyhole naturally brings to mind something small, a narrow opening that lets only a thin beam of light through. In astronomy, the concept is similar, but the scale is immense. A gravity keyhole is a narrow region of space where the gravitational forces of two massive bodies create a precise imbalance. Not a perfect equilibrium, but just enough asymmetry to redirect an object's future path without capturing it outright. For Jupiter, this keyhole sits near the outer edge of its Hill sphere, the vast region where Jupiter's gravity overtakes the Sun's. The Hill sphere spans millions of miles, yet embedded within that enormous boundary is a region only a few hundred kilometers across, a doorway carved into an otherwise smooth gravitational slope. This contrast in scale is why astronomers use the word keyhole. It is tiny relative to the surrounding space, almost impossibly so. If an object passes through this region, the choreography of gravity changes. Its trajectory bends in a predictable way. New orbital possibilities open. It is as if the object steps from one room into another in a house constructed entirely of gravitational forces. Nothing touches it. Nothing collides. And yet its future is altered. To grasp how unlikely this is, consider the geometry involved. The corridor leading toward Jupiter's keyhole is vast, many thousands of times wider than Earth. But the target itself, the region where the forces align just right, is only a few hundred kilometers across. It is like firing an arrow from Earth and threading it through a moving hoop attached to a jet halfway around the world. And even that analogy understates the difficulty. Because objects in space do not aim, they drift. Yet Atlas appears to be drifting toward that region. This is where the sense of wonder begins to grow. If Atlas enters the keyhole, it does not imply an impact. Jupiter is far too large, and the keyhole is far from its atmosphere. What it implies is something subtler. Jupiter's gravity could briefly capture small fragments if Atlas sheds material. A grain of dust, a sliver of ice, something light enough to slip into a temporary orbit while the main body continues onward. Atlas might move into what astronomers call a quasi-orbit, circling Jupiter loosely for a short period before escaping. Or it could pass through the keyhole cleanly, leaving behind faint dust signatures that remain detectable for weeks. In either case, Atlas could leave fingerprints. Those fingerprints could reveal composition, structure, and behavior in ways that Earth-based observation alone cannot. This kind of event is rare because it requires three factors to align with extreme precision: direction, speed, timing. If any one of these shifts slightly, the object misses the keyhole entirely. For a natural body like a comet, this level of precision almost never occurs. Outgassing alone, the tiny jets of evaporating ice that push on a comet's surface usually alter its path by far more than the width of a keyhole. Chaos usually dominates. Small forces accumulate unpredictably. But Atlas is quiet. Its outgassing is unusually low. Its trajectory noise is minimal. Its drift, after conjunction, when it emerged from behind the Sun, aligns with the direction of the corridor leading toward the keyhole. The razor-thin antitail provides a clear visual reference for orientation. The non-gravitational acceleration coefficients fit together into a pattern that makes this alignment physically plausible. None of this proves that Atlas will pass through the keyhole, but it makes the possibility worth careful attention. A simple image helps here. Imagine a pebble floating downstream. The current splits around two stones, leaving a narrow channel between them. For the pebble to enter that channel, every swirl and ripple must nudge it just right. The pebble does not aim, it drifts, but under the right conditions, drift is enough. That is the nature of a gravity keyhole. It is the flow of gravity converging into one improbable place. This is why the idea captivates scientists and observers alike. Not because it implies intention, but because it is mathematically elegant, a natural alignment that is both unlikely and precise, a doorway that almost no object finds by chance. An orbital analyst at the European Space Agency summarized it simply. A keyhole passage is improbable, but not impossible. Astronomers do not watch for impossibilities. They watch for outliers, for rare events that occur once in decades, for moments that prompt someone to step outside on a cold December night, look up, and wonder what is unfolding overhead. If Atlas threads this needle, even loosely, it will not vanish into the darkness immediately. Jupiter may retain clues. Dust distributions could change. Brightness could vary. The object's rotation might shift. These are signatures that Jupiter's gravity can amplify. For the first time, scientists might observe an interstellar object interacting directly with the gravity of another planet in real time, not through simulations or illustrations, but through data. That possibility alone is enough to fuel curiosity, a doorway only a cosmic sharpshooter could pass through. And yet, the trajectory we observe is drifting toward that doorway with unusual calm. Atlas is not the first unexpected visitor to our neighborhood. This pattern began earlier. For most of human history, the night sky appeared static. Stars held their positions. Planets traced slow, predictable arcs. Comets arrived and departed on long, familiar cycles. The solar system felt like a quiet district on the edge of a vast galaxy. Over the past 8 years, that image has changed, slowly at first, then unmistakably. In that short span, 3 objects from outside our solar system have passed through. 3 visitors, 3 outsiders. Before the year 2017, the number of confirmed interstellar objects was 0. The shift began with the one that changed everything. Oumuamua, detected in the year 2017, became the first confirmed interstellar object in recorded history. Nothing about it fit expectations. It showed no clear coma, no obvious dust tail, yet it experienced non-gravitational acceleration that could not be fully explained by conventional models. Its shape remained uncertain. Some interpretations suggested it was elongated like a cigar. Others proposed a flat, pancake-like form. The object never revealed the answer. It rotated, brightened, dimmed, and departed. It was in response to this data that Avi Loeb made his now well-known argument. He suggested that Oumuamua's behavior could be consistent with technological origin, not as a sensational claim, but as a scientific question. Half the astronomical community rejected the idea outright. Others remained unconvinced but cautious. What mattered most was that the debate began. For the first time, astronomers were forced to confront hard data from an object that did not originate in our own star system. That moment marked a change. The solar system was no longer a closed neighborhood. It was part of a larger flow, and Atlas is now the latest chapter in that unfolding story. 2 years after the first interstellar visitor rewrote the textbooks, another arrived. In the year 2019, astronomers detected a new object entering the solar system from beyond its boundaries. This one became known as Borisov. Unlike Oumuamua, Borisov behaved much more like what astronomers expected from a comet. It released dust. It developed a bright, visible tail. It showed a surrounding coma as sunlight warmed its surface. In many ways, it looked familiar, yet even Borisov carried surprises. Detailed analysis revealed that its composition was remarkably pure. The dust grains appeared crystalline and uniform, preserved in a condition that suggested they had remained largely untouched since their formation around another star. Most comets formed in our solar system experience repeated heating, collisions, and mixing over billions of years. Borisov seemed to have avoided much of that. It looked less like a weathered traveler and more like a pristine sample, an interstellar relic preserved almost exactly as it was at birth. Its tail, while clearly present, was also cleaner than expected. The dust did not show the usual broad spread of particle sizes. Instead, it appeared unusually consistent, as if the object had not undergone the violent internal mixing that characterizes most comets. If Oumuamua was an enigma that defied classification, Borisov was something else entirely. It was a time capsule, offering a glimpse into the chemistry of another planetary system with minimal alteration. This became the second confirmed interstellar visitor, the second hard data point. Now, in the year 2025, a third visitor has arrived. 3I Atlas, and it does not fit neatly into either of the previous categories. Like Borisov, Atlas has a tail, but the tail is unusually clean. It also forms an anti-tail, a feature that is rare but known. Yet this anti-tail is too thin, too stable, and too long-lasting to match typical examples. Atlas's trajectory fits within natural models, but the fit is unusually straight, unusually quiet, and marked by remarkably low noise for an active object passing relatively close to the Sun. In behavior, Atlas seems to sit between the first two visitors, or perhaps outside that range entirely. It is not as dusty and chaotic as Borisov. It is not as silent and ambiguous as Oumuamua. It appears balanced, structured, and restrained in a way that does not align cleanly with either extreme. 3 interstellar objects, 3 very different personalities. Each one tells a distinct story about the environments they came from and the paths they followed to reach us. From a statistical perspective, this alone raises questions. For billions of years, humanity observed the sky without identifying a single confirmed interstellar object. Then, within the span of less than a decade, 3 appear. Each one challenges expectations in a different way. One explanation is straightforward and widely accepted. Detection technology has improved dramatically. Surveys such as Pan-STARRS, Gaia, and the next generation of wide-field sky scans are far more sensitive than anything available in the past. Objects that once passed unnoticed are now being flagged and tracked. That explanation is valid, but it may not be complete. Astronomers are increasingly considering another possibility. The solar system may currently be passing through a region of the galaxy where interstellar material is more densely distributed, a dynamic crossroads, shaped by long-term stellar motion and the structure of the Milky Way itself. Streams of dust, rock, and debris from distant systems may sweep through this region in slow cycles. Material associated with the Orion Arm could be drifting past, carried by galactic tides that operate on timescales far longer than human history. If this is the case, interstellar objects may not be rare at all. We may simply have begun detecting them during a period when the galaxy is delivering more of them into our neighborhood. This does not imply anything technological or intentional. It implies motion. It suggests that the space between stars is active rather than empty, filled with material shaped by ancient processes of formation and destruction. The solar system, in this view, is not isolated. It is moving through a kind of interstellar migration highway. Even within this broader context, Atlas stands apart. Oumuamua was silent and ambiguous. Borisov was familiar but pristine. Atlas is something else. It is disciplined. Its motion is organized. Its behavior appears balanced in a way that neither fully chaotic comets nor completely inactive objects usually display. If the first two visitors introduced the idea of interstellar messengers, Atlas complicates the narrative. It does not reinforce a pattern. It disrupts it. 3 interstellar objects in less than 10 years. That alone is extraordinary. But it is not the number that holds attention. It is the differences between them. As Avi Loeb has remarked, we have entered an era of interstellar messengers. And as a scientist at the European Space Agency phrased it more cautiously, 3 visitors do not establish a trend, but they certainly establish a question. That question becomes sharper when the discussion widens beyond individual objects and turns toward the structure of the universe itself. When people think about strategy, they usually imagine human systems, politics, military planning, economics. But strategy does not belong exclusively to human thought. In the universe, gravity creates a landscape of its own, a terrain shaped not by borders or intentions, but by mass, momentum, and time. If you zoom out far enough, the solar system stops looking like a collection of planets and begins to resemble a map, a terrain of deep gravitational valleys, high plateaus, and narrow passes, all of it carved by gravity. This perspective is sometimes referred to casually as cosmic strategy, not because the universe plans, but because its structure naturally creates regions of advantage and pathways of influence. In this framework, the Sun occupies the center. It is the capital, the dominant source of mass and energy. Everything orbits it. Everything depends on it. Jupiter occupies a very different role. It holds the high ground. Its gravity well is so deep and so wide that it shapes the behavior of the entire outer solar system. Earth, by comparison, sits in a stable mid-region, habitable and calm, but without commanding influence beyond its immediate neighborhood. Once you begin to see the solar system this way, another realization follows. Space contains choke points. Just as mountain passes control access between valleys on Earth, the solar system contains regions where motion becomes easier or harder depending on alignment and timing. These are the Lagrange points, labeled L1 through L5, gravitational pockets where forces balance just enough for objects to linger. Spacecraft use them. Dust accumulates there. Small asteroids can remain stable for long periods. They function like footholds in the gravitational terrain. Beyond these well-known regions lies Jupiter's keyhole, a gravitational gate positioned near the edge of Jupiter's hill sphere, a place where an object can, with extraordinary precision, slip into Jupiter's domain through a narrow corridor. Farther out still, near the boundary of the Kuiper belt, lies another transition region, a zone where the sun's influence begins to weaken and the gravitational currents of the galaxy start to dominate. This boundary functions like an outer border post, marking the shift from the ordered inner system to the more chaotic frontier. Together, these features form what physicists call natural corridors. They are not visible roads or tracks. They are regions where mathematics favors motion, where trajectories stabilize, where momentum carries objects smoothly instead of violently redirecting them. Space is not uniform. Some paths are easier than others. Some regions funnel motion, others scatter it. Atlas appears to be moving along one of the rarest corridors of all. That is what makes it remarkable. Nature, especially when dealing with active icy bodies like comets, is rarely precise. Outgassing disrupts alignment. Solar radiation pressure pushes unevenly. Small forces build into large deviations. Precision tends to dissolve over time. Yet Atlas is slipping into a gravitational corridor that most objects miss by millions of kilometers. If the solar system is a strategic map, the Sun holds the center, Jupiter commands the high ground, and Neptune guards the distant frontier. The moons, rings, Trojan swarms, and Lagrange regions act as outposts and reservoirs. Interstellar objects are the outsiders, arriving from beyond the mapped terrain, shaped by forces we only partially understand. When an interstellar object approaches a strategic position, especially one as narrow and consequential as Jupiter's keyhole, astronomers take notice, not because it implies intention or design, but because it is unusual. In human terms, a traveler passing quietly through a remote mountain pass would draw attention. In cosmic terms, an interstellar object aligning with a rare gravitational gate deserves careful observation. This does not mean the universe has plans. It does not imply motives or desires, but it does have structure. And structure creates pathways. Some paths attract, some resist, some narrow into channels so delicate that only the calmest trajectories can follow them. Atlas is approaching one of those channels. That alone makes it worthy of patient, careful, and respectful study. This is the deeper layer beneath tonight's story. It is the layer that speaks less to urgency and more to perspective. The kind of perspective that tends to resonate most with people who have lived long enough to see how often simple explanations fail. It begins with the recognition that the solar system is not random terrain. It is shaped, sculpted, and defined by gravitational architecture in much the same way continents are shaped by tectonic forces on Earth. Nothing about its structure is accidental. Over billions of years, mass and motion have carved out patterns that persist, repeat, and quietly govern how objects move. Gravity, in this sense, is not merely a force. It is a framework. As physicist Michio Kaku once described it, gravity is the architecture of the universe. Carl Sagan echoed the same idea in more accessible language when he said that we live in a cosmos shaped by forces we barely understand. These statements are not poetic exaggerations. They are practical descriptions of how order emerges from motion over immense spans of time. Seen through this lens, Atlas is not traveling through empty space. It is moving through a landscape, and within that landscape, it is not merely another comet passing through on a random trajectory. It is an object entering a rare and meaningful position, a position that has existed for billions of years, defined by gravity long before Atlas ever arrived, waiting quietly for something to pass through it. This perspective changes the emotional tone of the event. It replaces fear with curiosity. It replaces urgency with patience. If the solar system contains choke points, if gravity shapes corridors and lanes the way mountains shape rivers and valleys, then it becomes reasonable to ask a simple question. If these roots exist, why is Atlas using one? And if Atlas is navigating this gravitational architecture, how is it maintaining such a clean, stable path while doing so? There are moments in astronomy when data behaves differently than expected. The background noise drops, scatter tightens, patterns appear where randomness should dominate. When that happens, careful scientists do not jump to conclusions. They do not rush toward dramatic explanations. Instead, they widen the frame. They slow down the analysis. They examine possibilities that normally sit at the edges of discussion. This is one of those moments. Atlas, with its unusually stable vector drift and its razor-thin, persistent anti-tail, invites a question that is quiet but profound. What kinds of forces can move an object through space without leaving a visible trail of disruption? This is not a claim. It is an examination. Science advances not by asserting answers, but by testing models against observations and eliminating those that fail to match reality. When familiar explanations begin to strain, even slightly, the responsible response is not to invent new answers, but to expand the list of mechanisms under consideration. One of the quietest mechanisms ever proposed in physics is the solar sail. A solar sail does not burn fuel. It does not release gas. It does not produce heat, light, or exhaust. It operates on a simple principle: photons, particles of light, carry momentum. When they strike a surface, they transfer a tiny amount of force. That force is extremely small, but it is steady. Over time, it accumulates. If a large, thin surface is oriented correctly, the resulting acceleration is smooth, continuous, and highly directional. A solar sail can, in theory, produce a stable vector drift without turbulence. It can explain a straight trajectory without noise. No one is suggesting that Atlas is a solar sail, but when scientists search for mechanisms that apply force without chaos, sail-like effects naturally enter the discussion because they mirror the shape of what is observed. Another mechanism that remains entirely within established physics involves magnetic interaction. A magnetic sail does not rely on light. It interacts with the solar wind, the constant stream of charged particles flowing outward from the sun. By generating a magnetic field, an object can experience pressure from those particles. The force involved is small, but continuous. Unlike combustion or outgassing. Magnetic interaction produces no visible plume. It does not significantly heat the object. It simply alters momentum over long periods. If Atlas contained metallic components, or even a partially conductive core fragment, magnetic interaction with the solar wind could subtly shape its drift. And importantly, magnetic effects would not necessarily appear in optical data. There would be no glow, no obvious emission, only a trajectory that adjusts smoothly over time. There are also explanations that rely on much more familiar physics. Micro-adjustment jets. For example, even a single consistent vent on one side of an object can produce tiny directional nudges. Over weeks, those nudges accumulate. Most comets do not display this behavior cleanly because their surfaces are irregular. Jets turn on and off. Rotation changes orientation. Thermal stresses fracture the surface. The result is chaos. But if an object's internal structure were unusually uniform, or if its surface vents were arranged symmetrically, the outcome could be very different. A dense fragment, perhaps originating from a planetary core rather than a loose, icy aggregate, would rotate with greater stability. Its center of mass would remain fixed. Outgassing, if it occurred, could produce consistent rather than erratic acceleration. The resulting motion would appear disciplined rather than noisy. There are also explanations that require no unusual mechanisms at all. A dense rocky or metallic nucleus would naturally resist the chaotic effects of outgassing. Heavy dust grains would form a thin, stable anti-tail that resists dispersion by solar radiation pressure. A particularly favorable post-conjunction viewing geometry could reduce apparent jitter in orbital fits, making the trajectory appear cleaner than it truly is. None of these explanations require engineering. They require only the right combination of mass, composition, orientation, and timing. So why even consider quiet technological analogies? Not because anyone is searching for artificial objects, but because analogies help describe form. They give language to anomalies. A trajectory that is too smooth for an active comet. A drift that is too stable for thermal forces alone. These comparisons help scientists define the boundaries of the problem. They are descriptive tools, not conclusions. As Avi Loeb has emphasized repeatedly, ignoring anomalies is how learning stops. The purpose of science is not to protect existing models, but to test them against reality. NASA's own navigation teams acknowledge this balance. As one analyst at the Jet Propulsion Laboratory has noted, outgassing can mimic many effects, but not all. When nature produces behavior that approaches the edge of expectation, the responsible response is neither denial nor sensationalism. It is careful exploration. This is the heart of quiet speculation. Wonder without panic. Curiosity without commitment. No one is being asked to believe anything extraordinary, only to recognize that precision, in any context, deserves attention. A propulsion mechanism that leaves no visible trail is observationally indistinguishable from a perfect natural alignment. And when a line in the sky is this straight, the beauty lies in understanding why. Whether Atlas is entirely natural or partly shaped by forces we do not yet fully understand, its movement is elegant. Its anomalies are gentle, not alarming. They whisper rather than shout. They invite examination rather than reaction. For a moment, they allow us to stand at the edge of possibility, not because we expect revelation, but because we understand how rare such precision truly is. This brings us to a question that is rarely asked out loud. Not why Atlas exists, but why now? If you step back and look at the year 2025 from a perspective measured in time rather than geography, a subtle alignment appears. Atlas is not arriving in a random year. This is a moment when our tools, our technology, and even the sun itself align in a way that makes an event like this visible in ways it never could have been before. The question is not why Atlas came now. The question is why now is the moment when we can finally see Atlas clearly. Part of the answer lies with the sun. We are near the peak of solar maximum, the phase of the sun's roughly 11-year cycle when activity intensifies. Solar flares become more frequent. The solar corona brightens. The solar wind grows stronger and more variable. For most people, this results in stronger auroras at higher latitudes. For astronomers, it changes the observational environment. A stronger solar wind enhances interactions between charged particles, dust, and light. Tails become more defined. Anti-tails, especially thin dust plains, stand out more clearly against the background sky. When Atlas emerged from behind the sun, increased solar activity did not conceal its features, it amplified them. Structures that might have remained invisible during solar minimum became detectable because the environment itself was more dynamic. The other part of the answer lies with our instruments. A new generation of observatories has transformed how the sky is observed. The Vera Rubin Observatory, formerly known as the Large Synoptic Survey Telescope, is preparing to conduct an unprecedented deep survey of the entire sky. Its design allows it to detect objects hundreds of times fainter than previous systems and to track their motion night after night. The James Webb Space Telescope has already reshaped understanding of distant galaxies and planetary systems. Its sensitivity allows astronomers to cross-check brightness variations and compositional signatures with a level of precision that was impossible just a decade ago. Gaia continues to refine stellar positions to micro-arcsecond accuracy, providing the stable reference frame needed to measure extremely small changes in Atlas's trajectory. On the ground, thousands of smaller telescopes operated by universities and amateur astronomers now use artificial intelligence-based stacking and deconvolution software. Hundreds of individual exposures are combined. Noise is removed systematically. Faint structures emerge with clarity. The gap between professional and amateur observation has narrowed in ways few predicted. All of these factors converge on a single conclusion. We are not witnessing a new universe. We are witnessing the same universe with better eyes. The sky has not changed. Our ability to read it has. Atlas is not performing on a new stage. The lights have simply grown brighter, and in that brighter view, a quiet object from another star system reveals itself with unusual grace, moving through a gravitational landscape that has always existed, patiently waiting to be seen. An artificial intelligence system has quietly become one of the most influential tools in modern astronomy. Not in the dramatic way, often imagined in popular culture, and not as a replacement for human reasoning or scientific judgment. Its role is far more restrained, but no less important. Artificial intelligence now performs the patient, repetitive, and highly precise work of cleaning astronomical data, a task that once consumed enormous amounts of human time and still left critical details unresolved. Astronomical observations are never clean by default. Light from distant objects passes through Earth's atmosphere, where turbulence bends and scatters it. Temperature gradients distort images. Water vapor absorbs specific wavelengths. Even the most advanced telescopes collect data filled with noise, artifacts, and errors introduced by sensors themselves. For decades, astronomers relied on careful calibration, averaging techniques, and manual inspection to extract meaning from this chaos. Progress was steady, but slow. Artificial intelligence has changed this process fundamentally. Modern systems are trained to recognize the difference between signal and noise across thousands of parameters simultaneously. They remove atmospheric distortion, frame by frame. They correct subtle optical aberrations that would once have been ignored as unavoidable. They enhance faint linear features that dissolve into the background in traditional imaging. They compare blurred frames across multiple nights and predict how an object should move, allowing them to recover motion that once vanished into uncertainty. This capability reshapes what can be observed. Objects that would have disappeared after a single night can now be tracked for weeks. Tails that once appeared amorphous can be resolved into structured flows. Anti-tails, which depend on extremely precise geometry, become visible and measurable. Vector drift, once lost in statistical scatter, emerges as a coherent signal. These improvements are not cosmetic. They change the scientific meaning of what we see. If Atlas had passed through the solar system in the year 2010, it likely would have been catalogued as an unremarkable smudge. If it were noticed at all, its structure would have remained ambiguous, its tail unresolved, its anti-tail invisible, its trajectory uncertain. In the year 2025, the same object appears in detail. Its dust geometry is visible. Its anti-tail persists across multiple observing cycles. Its vector drift is measured rather than inferred. The difference is not Atlas. The difference is us. There is a quiet philosophical truth embedded in this shift. Atlas did not suddenly become interesting. The universe did not change its behavior. What changed was our ability to perceive, not visible to Atlas, but visible to ourselves. Humanity reached a level of observational maturity where details that had always existed could finally be detected, measured, and understood. We did not become special. We became capable. The timeline reinforces this point. The first confirmed interstellar object was detected in the year 2017. The second followed in 2019. The third appeared in 2025. All three discoveries occurred during the era of automated sky surveys, continuous monitoring, and machine-assisted analysis. It is increasingly likely that interstellar objects have passed through the solar system for billions of years without notice. The difference now is constant vigilance. Today, the sky is monitored around the clock. Automated surveys scan vast regions nightly. Motion detection algorithms flag anything that deviates from expected orbital patterns. Artificial intelligence systems compare observations across time and space. Very little slips through unnoticed. This realization leads to an important conclusion. Atlas is not the culmination of a rare sequence. It is an early example of a new era. In the coming decades, astronomers expect to identify many more interstellar visitors. Some will be fragments of distant planetary systems. Others may be relics of stellar nurseries, preserved in cold interstellar space for eons. Some may be icy wanderers that crossed light years before briefly entering the sun's domain. The solar system may not be a quiet backwater. It may be a crossroads, a region where gravitational dynamics funnel material more often than previously assumed. In that context, Atlas becomes more than a comet. It becomes a marker, a signpost indicating the moment when humanity gained the tools necessary to observe the galaxy as an active, evolving environment rather than a static backdrop. As Neil deGrasse Tyson observed, we are finally seeing the universe with the resolution it deserves. With that understanding in place, attention naturally turns forward to a specific moment in time, March 16th. If you have followed Atlas's journey from the beginning, you may have noticed how quietly that date has gained importance. There has been no dramatic countdown, no warnings, no urgent headlines. Instead, there has been a slow tightening of focus. Atlas has traced a path so steady and so disciplined that March 16th has become a milestone. Not a moment of danger, not a moment of spectacle, a moment of clarity. On March 16th, in the year 2026, Atlas will reach its point of closest dynamic interaction with Jupiter. The phrase dynamic interaction is precise for a reason. This is not an impact trajectory. Jupiter is enormous. If Atlas were on a collision course, that fact would have been clear months earlier. Instead, Atlas will pass far outside Jupiter's physical body. Distance is not the story. Influence is. For a limited window, Jupiter's gravitational field will exert a measurable effect on Atlas. This influence will be gentle, predictable, and fully described by gravitational physics. From this interaction, 3 outcomes are possible. All are calm. All are expected within known science. The first and most likely outcome is a simple pass. Atlas skirts the outer edge of Jupiter's Hill sphere and continues onward. This is the fate of most interstellar comets. They enter a planetary system, experience a modest deflection, and depart back into interstellar space. In this scenario, Atlas would remain largely unchanged. Its trajectory would curve slightly. Its brightness would slowly fade. Nothing dramatic would occur. The second possibility is more interesting but still routine. Atlas enters the broader gravity corridor associated with Jupiter but misses the keyhole itself. In this case, Jupiter's influence would be stronger. Atlas's outbound trajectory would be more noticeably altered. It would be redirected onto a new path shaped by Jupiter's gravity. This is the scattering effect giant planets exert on passing objects. Atlas would then drift outward for years or decades, gradually becoming too faint to observe. The third possibility is the rare one. Atlas passes through the gravity keyhole. This scenario draws attention not because it is dangerous, but because it is informative. A keyhole passage does not pull Atlas into Jupiter. It allows Jupiter to influence Atlas in a highly specific way. If Atlas sheds even small amounts of material during this passage, individual grains could be temporarily captured. Those grains might orbit Jupiter briefly before dispersing. In effect, Jupiter would store samples from another star system within its gravitational domain. This would be a scientific opportunity. Natural material from beyond the solar system, briefly held where it can be studied indirectly through reflected light and spectral analysis. No spacecraft required. No intervention. Just gravity doing what it does best. Why does this possibility matter? Because Atlas's approach is unusually tidy. Its trajectory is cleaner than expected. Its vector drift aligns with the gravity corridor. Its anti-tail indicates a stable orientation. None of these factors guarantee a keyhole passage, but together, they make the alignment worth careful attention, not with excitement, but with concentration. What will actually be observed on March 16th? Not a visual spectacle. There will be no flash or sudden transformation. Instead, astronomers will measure extremely small changes, tiny shifts in velocity, slight adjustments in trajectory, subtle variations in brightness, minute changes in orientation. This is a scientific moment, not a cinematic one. It rewards patience rather than anticipation. The significance goes beyond the event itself. If Atlas passes through the keyhole, models of interstellar dynamics gain a rare data point. Scientists learn how objects migrate between gravitational domains. If it misses, that outcome is still valuable. Atlas becomes one of the cleanest examples of near-keyhole alignment ever recorded for a natural object. Either result advances, understanding. This is not a moment to fear. It is a moment to observe, a moment when the universe speaks quietly, a moment where precision itself is the story. March 16th is not about danger. It is about gravitational geometry, about how a distant icy traveler interacts with the deepest gravitational well in the outer solar system. It is a reminder of how fortunate it is to witness this with modern instruments. Careful analysis and a sense of perspective shaped by time and experience. For you, listening quietly, this moment is meant to feel grounded, calm, like watching a rare migration pass through a familiar valley. Something fleeting, something natural. You do not brace for impact. You simply observe. As the dynamics team at the Jet Propulsion Laboratory has stated, a keyhole passage is a scientific gift, not a threat. To appreciate that fully, it helps to return to the deeper feeling beneath this entire story. As the journey continues, the intensity softens, the sharp edges fade, because what you have been hearing is not a warning. It is not a crisis. It is a window, a brief opening into a universe that is vast, structured, and profoundly calm. There is a quiet truth at the heart of astronomy. Fear and awe are not the same emotion. Fear arises when the mind imagines threats that do not exist. Awe appears when you encounter something immense and realize it makes no demands of you at all. Atlas belongs entirely to that second category. It does not threaten. It does not intrude. It simply moves, gracefully, predictably, following gravitational architecture that has governed this region for billions of years. In that way, Atlas becomes a gentle lesson from the cosmos, not a message, not a sign, just a reminder of how much there is to observe, and how peaceful understanding can be when we take the time to look carefully. For all the discussion surrounding trajectories, gravity corridors, and keyholes, one central fact remains unchanged. Nothing Atlas is doing poses any danger to Earth or to the structure of the solar system. It is not disrupting orbital stability. It is not altering planetary dynamics. It is not introducing any new risk. Atlas is simply an interstellar object moving through a gravitational environment that has existed for billions of years and will continue to exist long after it has passed through. The unusual features in its path are not warnings. They are observational opportunities. What makes Atlas noteworthy is not that it threatens anything, but that it allows scientists to observe a rare configuration of motion with an unprecedented level of detail. This distinction matters because it separates scientific curiosity from unnecessary alarm. To appreciate that difference, it helps to place the event in historical context. For nearly all of human history, people lived and died without knowing that material from other star systems could pass through our own. The night sky appeared local. Stars were distant but fixed. Planets followed predictable paths. Comets were understood as members of the solar system, bound to the sun on long elliptical orbits. The idea that objects from beyond the solar system might visit us remained theoretical. That changed only recently. Even a few decades ago, an object like Atlas would have appeared as little more than a faint point of light, difficult to track and easy to lose. Its fine structure would not have been resolved. Its anti-tail would have gone unnoticed. Its subtle vector drift would have been indistinguishable from measurement noise. Atlas would not have become a subject of extended analysis. It would have been catalogued briefly, if at all. What has changed is not the object, but our capacity to observe it. Advances in wide-field surveys, precision astrometry, and data processing now allow astronomers to follow faint interstellar visitors with continuity and confidence. Features that were once inaccessible are now measurable. Patterns that once dissolved into uncertainty can now be tracked across weeks and months. This shift represents a broader transformation in astronomy. The field has entered a phase where detection is no longer limited by occasional observation, but supported by continuous monitoring. Automated surveys scan the sky nightly. Algorithms identify motion against dense star fields. Artificial intelligence assists in separating signal from noise. As a result, objects that once passed unnoticed are now recorded, analyzed, and understood. Seen this way, Atlas is not the conclusion of a rare sequence. It is an early example of a detection era that is only beginning. As observational coverage improves, astronomers expect to identify more interstellar objects in the coming years. Some will resemble classical comets. Others may not. Some may be pristine remnants of distant planetary systems. Others may be fragments altered by long exposure to interstellar space. This growing sample will allow scientists to move beyond isolated case studies and begin asking statistical questions. How common are interstellar visitors? What range of compositions do they exhibit? How do their trajectories interact with planetary gravity? Atlas contributes to that future dataset, not by being dramatic, but by being precise. Attention now naturally shifts toward a specific moment in Atlas's journey. March 16th. This date has acquired significance not because it marks a moment of risk, but because it marks a moment of measurement. On March 16th, in the year 2026, Atlas will reach its point of closest dynamic interaction with Jupiter. This phrasing is deliberate. Atlas will not approach Jupiter's physical surface. It will pass far outside the planet itself. What matters is the extent of gravitational influence, not physical proximity. During this period, Jupiter's gravity will exert a measurable effect on Atlas's trajectory. That effect will be gentle, predictable, and fully consistent with established gravitational theory. From this interaction, 3 broad outcomes are possible, all of them expected within known physics. The most likely outcome is a straightforward pass. Atlas approaches the outer boundary of Jupiter's Hill sphere, experiences a slight deflection, and continues on an outbound path into interstellar space. This is the typical behavior of interstellar objects encountering a massive planet. In this scenario, Atlas remains largely unchanged aside from a modest adjustment to its trajectory. A second possibility involves a stronger interaction. Atlas enters the broader gravitational corridor associated with Jupiter, but misses the narrow keyhole region. In this case, Jupiter's influence redirects Atlas more noticeably, altering its outbound trajectory. This is a common scattering process by which giant planets reshape the paths of passing objects. Atlas would then depart the solar system on a new trajectory, gradually fading from observation. The third possibility is the least likely, but the most scientifically interesting. Atlas passes through the gravity keyhole itself. A keyhole passage does not imply capture or collision. Instead, it allows Jupiter to influence Atlas's motion in a very specific and constrained way. If Atlas releases small amounts of material during this passage, individual dust grains could be temporarily retained within Jupiter's gravitational domain. These grains would not remain indefinitely, but their brief presence could provide valuable information about Atlas's composition and structure. This possibility draws attention not because it is dramatic, but because it would offer a rare observational opportunity. Natural material from another star system interacting directly with a planetary gravity field provides insight that simulations alone cannot supply. What makes this scenario worth monitoring is the manner of Atlas's approach. Its trajectory is unusually clean. Its vector drift shows minimal noise. Its alignment with the gravitational corridor is precise. Its anti-tail suggests a stable orientation. None of these factors guarantee a keyhole passage. However, together they justify close observation. What astronomers expect to observe around March 16th is not a spectacle. There will be no sudden brightening or abrupt change visible to the unaided eye. Instead, scientists will examine small deviations in motion, subtle changes in brightness, and minute adjustments in trajectory. This is a moment defined by measurement rather than appearance. Regardless of the outcome, Atlas will contribute meaningful data. A keyhole passage would provide direct insight into gravitational migration across planetary boundaries. A near miss would still represent one of the clearest examples of close keyhole alignment ever recorded for a natural object. Both outcomes improve understanding. Importantly, none of these scenarios involve danger. They unfold far from Earth and within well-understood physical limits. Atlas's motion is governed by the same gravitational principles that maintain planetary stability throughout the solar system. As the analysis progresses, it becomes clear that the significance of Atlas lies not in threat, but in perspective. It highlights how far observational astronomy has advanced. It demonstrates how subtle features can now be detected and interpreted. It reminds us that the solar system is not isolated, but part of a larger galactic environment through which material flows. Atlas also illustrates an important point about scientific progress. Discovery does not always come from dramatic events. Often, it comes from clarity, from the ability to see patterns that were previously obscured, from patient observation rather than urgency. Every aspect of Atlas's behavior, from its trajectory to its brightness variations, follows known physical laws. Those same laws govern Earth's orbit, stabilize planetary systems, and allow life to persist. Atlas does not challenge that framework. It reinforces it. To observe an interstellar visitor passing quietly through the solar system is not a cause for concern. It is an opportunity to expand understanding. Out of all the centuries of human observation, This is the period in which such events can be documented with precision. That is not something to fear. It is something to recognize as a milestone in scientific capability. Atlas will continue on its path, unaffected by attention or interpretation. Jupiter will maintain its orbit, shaping the outer solar system as it has for billions of years. The broader structure of the solar system remains unchanged. What changes is what we learn. In that sense, Atlas is not a warning or a message. It is a case study, a quiet demonstration of gravitational order, observational progress, and the expanding reach of human knowledge. Seen from this broader perspective, Atlas becomes a reference point rather than an exception. It represents a moment when observation, theory, and timing briefly align, not to deliver a revelation, but to refine understanding. In astronomy, progress rarely arrives as a single dramatic answer. It accumulates through cases like this, where one object behaves just clearly enough to test models that were previously abstract. Atlas also reminds researchers that the solar system is an open system. It exchanges material, energy, and momentum with its galactic environment. Interstellar objects are not intruders. They are participants in a larger circulation of matter shaped by gravity on scales far beyond any single star. Each visitor carries information about conditions elsewhere, preserved across immense distances and times. From a scientific standpoint, the value of Atlas lies in its restraint. Its motion is not chaotic. Its features are not exaggerated. That makes it useful. Clean data allows cleaner conclusions. A trajectory with low noise sharpens orbital models. A stable dust structure constrains assumptions about composition and internal structure. Even the absence of dramatic behavior becomes informative, narrowing the range of plausible explanations. As additional interstellar objects are discovered in the coming years, Atlas will serve as an early benchmark. Future observations will be compared against it. Differences will be measured. Patterns will be tested. What now appears unusual may later become part of a broader distribution, or Atlas may remain an outlier. Both outcomes are valuable. What matters is that this event demonstrates how modern astronomy works at its best. Careful measurement, conservative interpretation, willingness to note anomalies without inflating them, confidence in physical laws paired with openness to refinement. This balance is what allows understanding to deepen without drifting into speculation. In the end, Atlas does not ask to be interpreted beyond what the data supports. It does not demand narrative. It does not require meaning. It simply moves through space, following gravity, offering a brief window into processes that usually remain abstract. That is enough. The solar system continues unchanged. Jupiter remains a dominant gravitational anchor. Earth remains stable, and somewhere beyond the planets, Atlas continues on a trajectory set long before it was ever observed. What remains after it passes is not disruption, but knowledge. A clearer picture of how interstellar matter behaves when it encounters a planetary system like our own. That clarity is the real outcome of this encounter. Not answers to every question, but better questions, grounded in observation. And that is how science moves forward.